All right, thanks everybody. I am Kent Sorenson, Chief Technology Officer at Allonnia. We are a bioingenuity company really taking inspiration from nature and especially biology to work to solve some of the world's most challenging environmental issues. I am MIT graduate student from further back than I care to admit, especially after the last few presentations, but it has been a while. But Allonnia was also a spin out of Ginkgo Bioworks, which is another MIT startup. So a couple of connections there. So while we're working on a number of different environmental challenges, I really want to focus on sustainable mining and metals and specifically bioextraction of rare earths. This is one of the things that we're advancing fairly rapidly just in the last year. And you've heard a lot this morning about demands for electricity and needs for electrification, particularly in terms of decreasing carbon emissions. Well, you can't do all of that today without a lot more metal. So specifically the rare earth elements and what the Department of Energy calls critical materials or critical minerals, things like copper, lithium, cobalt, et cetera, nickel, we need a lot more of those metals. So how do we mine those sustainably, considering that the mining industry is something like 10 to 20% of global carbon emissions today, depending on how you do that accounting. So we'd like to decrease that while still meeting the electrification needs. One way to do that is to upcycle waste, certainly, but we also, from a security standpoint, need domestic supply chains of these materials. And currently, 90 to 95% of the rare earth global supply is controlled by China using a very environmentally intensive, chemical intensive process to separate those rare earths. And so we'd like to decrease the environmental footprint, but also secure domestic supply chains. So we're focused on recovering REEs from potentially a variety of different waste streams. We are also looking at copper and other critical materials. But clearly, using biology, we want to decrease the volume of toxic reagents, but also, as has been pointed out by some of the other presenters here, do this in a way that is a little more plug and play to reduce CapEx costs and allow for faster return on investment. So what specifically is the technology? Well, we are using proteins, and as a benchmark, we have a protein called landmodulin, which we can attach to beads and put in a column very similar to an ion exchange column. And when we run water through those beads with the rare earth metals, and specifically these are some of the lanthanide metals, what you see is really interesting because biological proteins are very good at sequestering very specific metals because they either need them for metabolism or to reduce toxicity or a variety of other biological processes. So you have all this other metal that's in water like acid mine drainage, that's passing directly through the column with no sorption to our protein or our beads. The three rare earths are the lines here. You see about 30 to 40 bed volumes before we start to see breakthrough of those. So we're seeing really good specific sorption of those compounds in that column. And then what's great is when we elute the metals off of that, we're getting a concentration of about 10 to 45x with some of our preliminary data here at something north of about 90% purity for those mixed rare earths. So very, very different solution coming out than went in. Now, where we go from here is we're partnered with a global mining company already at a US mine site, actually a copper mine, for initial testing with a mine impacted water that looks something like the one in the picture that's only about less than 10 parts per million of rare earths, but has thousands of parts per million of things like iron and aluminum and other competing metals. So we want to remove those, and we're very excited that we are seeing now some very good pre-treatment results that allow us to easily remove things like aluminum and iron. And then in the previous chart, I already showed you how calcium, magnesium, and a lot of other metals that are in that material go right through the column. And what we're showing on the bottom here is in addition to that, we're able to see multiple cycles of reuse of the protein. So we can regenerate the protein. Right now, we've got no loss of capacity after 5 cycles of sorption and desorption. When you get to about 10 cycles, you are starting to lose some capacity there, and this is where some of our protein engineering will come in. We do need to increase that to make the economics start to look really good, but it's very promising to be at this stage right now. We plan to go to the field in the first quarter of 2025 and actually be on the mine site doing this at a small scale, pilot scale. So we're certainly interested in partners who are end users, whether that's mining companies, energy companies, electronics companies, and defense also uses a lot of rare earths. We need access to more waste streams that contain these materials, so that could be e-waste, urban mining, other industrial waste streams, produced waters, for example, from the fracking industry have REEs in them. There's a number of different waste streams that have these metals in them. And of course, deployment partners. We're not going to be the whole solution. We're going to be part of an integrated system at some point. And so other partners who want to work with us on this are of great interest. And I've been focused on just the rare earth market, but just to let you know, we are also very much involved in emerging contaminants, especially PFAS treatment from water, as well as a couple of other sustainable mining solutions. So hope to see you. Stop by our table over in the other room, and thank you. Appreciate the time.